Swayam Prabha. Digital India. Educated India.
Okay, what we will now do is derive another form of Bernoulli's equation which is for irrotational flow. Okay. So, we have already derived Bernoulli's equation for inviscid flow which happens at a high Reynolds number, and they occur in regions away from the wall, okay, and which we call as inviscid flow. Now, we say in addition to that the flow is irrotational. What do you mean by that? This diagram is familiar to us. It shows a fluid element at time t and the same element at time t plus delta t. It can undergo normal strain rate, shear strain rate, also undergo rotation rate. Okay. Now, the condition what we are saying is that there is no rotation of the fluid element. When we say rotation, rigid body rotation of the fluid element, there can be change in length, there can be change in angle, which means there can be non-zero normal strain rate, non-zero shear strain rate, but rotation is 0. That is what we mean by irrotational. Okay. Okay. Fluid particles do not rotate, okay. That is what it means. Okay. How do you quantify it? We have seen vorticity is given by del cross V, the curl of velocity vector, and which we said as 2 times the rate of rotation vector, and the vorticity vector is equal to 0 vector. Okay. That is how we quantify irrotational flow. So, we said del cross V represents rotation, and now since we are considering flows which are inviscid and irrotational, okay. So, the vorticity is 0 vector. Okay. Okay. We started with the steady flow Euler equation. So, we will do here that as well. Okay. In fact, this derivation most of the part almost till one particular stage, this derivation is same as the last form of same as what we derived for the other form of Bernoulli equation. Okay. So, this is the steady state Euler equation, and then we used a vector identity and obtained this form of the equation. We used a vector identity for this term and then got this form of the equation, and of course, expressed gravity in terms of gradient, etc. We also divided by rho, which means the assumption of incompressible carries over here as well. So, till this stage whatever you have derived earlier applies here as well. Now, what we did next was we took a small differential length along the streamline and took a dot product of the right hand side and the left hand side with that vector, differential vector ds vector. Now, why did we do that? Our objective was to our idea was to make the right hand side 0, and because this vector v cross vorticity and the ds vector are perpendicular to each other, we took a small differential length along the streamline, took a dot product, so that right hand side is 0. Now, for the present case the right hand side is 0 automatically, because we have taken vorticity to be 0. Okay. In the earlier case we made the right hand side 0 after taking a dot product with a differential length along this streamline, but now right hand side is 0 anyway, because we are considering irrotational flow, okay, which means that the ds vector need not be along streamline. Even if you take along any line, the right hand side is going to be 0. Our idea of taking differential length along streamline was that to make the right hand side 0. Now, that necessity does not arise, because the vorticity 0, right hand side is anyway 0. Okay. So, ds need not be along streamline, it could be along any direction, okay, and this is what we are going to see in the next slide. Okay. So, let us recall what we have done for this Bernoulli's equation, the last two steps. We took the dot product with the ds vector, and then the right hand side was 0, and then we had these steps where ds vector was expressed in terms of dxi, dyj, dzk, and then we took an example of gradient of p, and then we saw the dot product was nothing but the differential, total differential of p dp. Okay. So, we could express this equation first in terms of differential, and then we said the sum of these three terms, namely pressure, kinetic and potential energy per unit mass is equal to constant along a streamline. And I also told you that we take 2 points which are very near, that is what the differential means, but they should be along the streamline. That is why this sum is a constant along a streamline. So, that is the case if we take only inviscid flow. Now, because we have taken irrotational flow also, now as we discussed in the previous slide, I need not take ds vector which is along a streamline, I can just take any vector. Okay. So, let us say this is our streamline, I can take any 2 points along any direction. Okay. So, this dA vector is such a small differential length once again, but along any direction. Why do we do that? Because this is 0. So, right hand side vorticity is 0 vector. So, right hand side is anyway 0. So, I can take 2 points along any direction. Now, what happens? If you repeat the same steps as we have done earlier, but instead of ds vector I have a vector some dA vector along any direction, once again expressed as dxi, dyj, dzk. For example, if you take gradient of p, if you take a dot product between gradient of p and dA vector, you once again get dp. So, once again you can express in terms of differentials of all the three energies, and the differential of all the sum of the energies is equal to 0, which means that the sum of the three energies, pressure, kinetic and potential energy per unit mass is a constant, but now along any direction, the A vector can be along any direction, and this sum is a constant along any direction. So, even purposefully I have not shown the derivation detail, because we should be able to arrive at this conclusion just based on physics itself, based on the condition that if it is irrotational, the right hand side is 0, statement number 1. Statement number 2, because right hand side is 0, I can take dot product with a vector along any direction, differential vector along any direction. So, immediately based on these two statements we should be able to conclude that the sum of these three energy terms is a constant along any direction. Okay. Okay, now what are the assumptions? Inviscid, that is anyway we started with Euler, steady state flow because we took the steady state form of Euler equation. Incompressible fluid, remember moment we bring in density inside the gradient in both the derivations, the density is taken as constant, which is incompressible fluid. Okay. And these three are common to both the derivations or both forms of the Bernoulli's equation. We have now seen two forms of the Bernoulli's equation. Now, what is the extra condition here, extra assumption? Irrotational flow, which means vorticity is 0. Okay. That is extra condition for the second form of Bernoulli's equation, okay, and which results in the statement that the sum of the energies, 3 energy terms, is a constant along any direction. That is same. This vorticity being 0 leads to the conclusion that the sum is a constant along any direction. If vorticity is not 0, if it is not irrotational, if it is rotational flow, then the sum of the energies is a constant along a streamline only, okay, streamline only, it cannot be constant along any direction. Okay. Though we said incompressible fluid, it is for incompressible flow also, just like we discussed our continuity equation. When I say what do I mean by incompressible flow? Incompressible fluid is something like water, flow of water. Incompressible flow is like flow of air at low velocities. Okay. So, it is applicable for that condition also. Okay. Now, I like to mention that if you look at a typical fluid mechanics book, Bernoulli's equation is discussed, let us say, the 3rd chapter, 1st chapter on fundamentals, 2nd chapter considers fluids at rest and rigid body motion, 3rd chapter itself Bernoulli's equation is discussed. How do they derive then is that they take a streamline, consider a movement of a particle along a streamline, they consider acceleration, which is our this term, okay, and then for the forces they consider only pressure force and then gravity force, that is all they consider, they do not consider viscous forces. That is what we have also done. Though we started with Navier-Stokes, we wrote down the Euler equation neglecting the viscous stresses. So, both have converged to the same physical significance, but the derivation is done in the beginning. Now, the derivation is once again done in the later part of the book as well, after deriving Navier-Stokes and the Euler equation, and that is the derivation we are discussing. Okay. We are not discussing the, of course in principle they are same. So, the methodology of derivation what we have adopted or what we have followed is available usually in the later part of the book. In the first part of the book it is taking a particle, looking at the forces, that is what we have done. We have also done indirectly. So, if you want in terms of reference, this derivation will be available in later part of the book. The derivation done in the first part of the book, in principle it is same, physically it is same, may look slightly different. Okay. Okay. Since we are discussing about a rotational, irrotational flow, I thought I will discuss this difference as well, nicely brought out in this book Sengal and Simbala. What we are going to discuss, what we are going to differentiate is between 2 types of circular flows. One is a rotational circular flow, other is a irrotational circular flow. Okay. So, let us look at the 2 figures here, it says flow A and flow B. What is shown here are streamlines and the velocity vectors. Okay. In this case, okay, because we are discussing circular rotational flow, we can't avoid polar coordinates, though we avoid it as much as possible. So, here what is shown here is u theta. What is u theta? Velocity in the tangential direction, velocity in the theta direction, okay, velocity in the theta direction, and that varies linearly with r, with the radial direction, and that is what is shown here, velocity varying linearly with r. And this is circular flow showing streamlines and the velocity vectors. Okay. Now, and let us show other look at the flow B, where once again it is circular flow, because the streamlines are circular, no doubt about it, but in this case the velocity once again the tangential direction in the theta direction varies inversely with r, and that is what is shown here. As you go away from the center, the tangential velocity decreases, or u theta and r is a hyperbolic form. Okay. That is what is shown here. So, flow A circular, flow B circular, and flow A the tangential velocity increases with r, flow B tangent velocity is inversely proportional to r, decreases with r. Okay. Now, if you identify a fluid element here, and if you look at the top view, what happens? It rotates along with the flow, that is what you see here. Okay. It is here, etc., but it is rigid body rotation, the whole body just rotates along with the flow. And to give a nice example, that is what this book does, what is shown here is a roundabout which is shown here, which of course children play, and if you look from the top view you can see them rotating along with the, of course this case it is not flow, along with the roundabout. Of course they undergo a rigid body rotation, of course just like they smile, here also you have smileys here which undergo rigid body rotation, and so this is a rotational circular flow. Now let us look at the other example. In this case if you identify a fluid element, okay, for a moment let us take the front view, that is a physical example also, then what do you see, they always stay upright, they always stay upright, they do not undergo any rotation, all of them are staying upright. Okay. Of course the smiling face, what is the physical example, ferry wheel or giant wheel, where if you look at the front view, of course whomever is there in, let us say in every position, they remain always upright. Of course they have to remain upright based on the configuration of this ferry wheel or giant wheel. So in this case once again it is circular flow, but the fluid elements remain always upright. So this is an example where circular flow, but it is irrotational. Okay. So the first case circular but undergoes rigid body rotation. In the second case, if you look at the orientation of a fluid element, it always remains upright, or if you look at this giant wheel, ferry wheel, the position of the people sitting in, let us say in every basket or whatever, they remain upright. Okay. So the good example to distinguish between circular rotational circular flow and irrotational circular flow.